Welcome back to the Deep Dive. Today we're really getting into something fascinating. We're cracking open a file marked Most Secret from the Depths of World War II. It details a hidden trial, a kind of engineering showdown, known only by its code name, Exercise Dracula.
That's right. And this wasn't, a battle with bullets and shells out on the front lines.
Yeah.
This was something different. It was this incredibly brutal, really systematic competition fought right there in Britain in the summer of 43.
Fought with what? Oil, torque, tools?
And a mountain of maintenance logs, absolutely. It pitted the two great allied industrial powers, Britain and the U.S., against each other through their tanks.
Okay, so more than just comparing tanks side by side.
Oh, much more. You've got to understand, Exercise Dracula, it was a fundamental reckoning for Britain, really. A national test.
A test of what, exactly?
It was designed, essentially, to determine if Britain's whole approach, this commitment to complex, high-performance, almost bespoke craftsmanship.
Right, the sort of traditional British engineering excellence idea.
Exactly. Could that possibly compete with the sheer, overwhelming, repeatable industrial power of the American manufacturing machine? That was a core question.
So we're diving into this specific showdown. It was Britain's big hope, the new Cromwell cruiser tank, against the, well, let's say less glamorous American workhorse, the M4 Sherman.
That's the one. And the stakes were huge. It wasn't just about which tank was better in a simple sense. It was about whose engineering vision would define the path to Allied victory.
Complex perfection versus rugged efficiency.
Precisely. And the result, well, it turned out to be a really profound and, frankly, quite humiliating lesson for British engineering pride at the time.
Humiliating, but maybe necessary. It reshaped logistics for the war, didn't it?
It absolutely did. So our mission today is to pull apart those secret reports, look at what happens when, national ego bumps up against cold, hard battlefield pragmatism.
And we're going to use the actual data from Exercise Dracula?
Yes, especially the maintenance data. The difference in maintenance hours required is just astonishing. It reveals this enduring truth about reliability, really, in any high-stakes, chaotic situation.
Okay, let's get into it. Part one, then. The British hope. The Cromwell. Right, so let's set the scene. We need to picture it. 1943. The location is Bovington Camp in Britain.
Which is basically the spiritual home of the British Tank Corps, isn't it?
Yeah.
Training grounds, development center.
Exactly. It's the heart of it all. And this is where Exercise Dracula kicks off. Britain at this point desperately needed a winner tank-wise.
Oh, desperately. They'd been plagued by tanks that were either too slow, too unreliable, or both. Tanks that just fell apart under the stress of combat.
So the Cromwell was meant to be the answer.
It was the promised solution. And you got to remember the context of British tank doctrine then. They had this two-tier system.
Right, the infantry tanks and the cruiser tanks.
Exactly. Infantry tanks, slow, heavy armor for breaking through enemy lines. Think Matilda, Churchill. And then cruiser tanks. They were meant to be the fast, maneuverable ones, like armored cavalry, designed to exploit breakthroughs, get behind enemy lines.
But the previous cruisers hadn't really worked out. I remember reading about the Covenant or the Crusader.
Total nightmares, many of them, notoriously unreliable mechanically, often breaking down before they even got to the battle. It was a huge problem.
So the Cromwell wasn't just another iteration. It was like, this is it. This has to work.
It felt like the final, maybe desperate attempt to actually deliver on that cruiser promise. So Exercise Dracula's goal was simple. Prove definitively that this new Cromwell tank was ready, that it was reliable, that it could operate across Europe.
There's a lot of writing on it then.
Yeah.
National honor, technological showcase.
Absolutely. It was intended to show the world, and maybe themselves, that Britain could still lead in tank design.
And looking at the specs, you can sort of see why they were hopeful, maybe even arrogant.
You can. On paper, the sources describe the Cromwell as a potential masterpiece. It looked the part, sleek, low profile, really built for speed. The performance metrics they were aiming for were amazing for 1943.
That 40 miles per hour figure stands out.
It does. That wasn't just fast for a tank, it was revolutionary. That's the kind of battlefield mobility the British doctrine was crying out for.
And the heart of this machine, the engine. That was the real showpiece, wasn't it?
It was. The Cromwell was powered by the Rolls-Royce Meteor engine.
Okay.
And this is where the ambition, the national pride, really comes into focus. Because the Meteor wasn't a brand new design from scratch. It was a derivative.
A derivative of what?
Of the Rolls-Royce Merlin engine.
Wait, the Merlin. The Spitfire engine.
The very same legendary engine that powered the Spitfire fighter plane, the icon of the Battle of Britain. They took that engine and adapted it for a tank.
Wow. Okay, that sounds impressive, but also maybe problematic. Taking an aircraft engine and putting it in a tank.
And that's precisely where the technical brilliance met the inherent risk. The Merlin, and therefore the Meteor, was an absolute jewel of engineering. High performance, high precision.
Built for the sky.
Exactly. Built for operating in the clean, cold air miles up. It thrives on high RPMs, designed for speed and altitude. It wasn't fundamentally designed for the low-speed, high-torque grind needed to push a 30-ton metal box across rough, muddy ground.
It's like taking a Formula One engine and sticking it in an off-road truck, isn't it? You're just asking for trouble.
That's a great analogy. You immediately introduce massive points of potential failure. What specific challenges does that pose? Well, you're trying to translate air superiority tech into ground-level durability.
Okay, so what were the main issues?
You're looking at two big ones, primarily. First, heat stress and torque management.
Right. Aircraft engines, especially liquid-cooled ones like the Merlin Meteor, rely on very precise temperature control and tolerances. Tanks generate immense heat just moving slowly.
Exactly. Driving a tank requires huge amounts of torque, especially at low speeds. That puts enormous strain on the transmission and the gearbox, generating incredible heat. The Cromwell's gearbox, which had to be incredibly complex to handle that power transfer from a high-revving engine,
It became a weak point.
became a massive vulnerability. Prone to overheating, prone to failure.
Okay, that's one. What was the second main issue?
Dust and dirt. Simple as that.
Spitfires fly in clean air.
Tanks operate in clouds of dust, mud, grime. It's unavoidable. That precision-engineered Meteor engine with its super tight tolerances designed for clean air and filtered fuel. It just couldn't cope with the abrasive reality of battlefield conditions without constant, meticulous servicing and filtering. It led to rapid wear.
So the very thing that made it brilliant in the air made it fragile on the ground.
In essence, yes. The British strategy was clear, though. Achieve the absolute peak performance no matter how complex the engineering needed to be.
And the sources confirm, the explicit goal was for the Cromwell to outclass anything the Americans had built.
That was the aim. Relying on that tradition of meticulous, bespoke craftsmanship, they genuinely believed that superior, more complex engineering would automatically translate into battlefield dominance.
They were willing to pay the price in complexity, assuming the performance payoff would be worth it.
They were. So that's the Cromwell. Fast, technologically advanced, carrying the pedigree of the Spitfire, representing the peak of British bespoke engineering, but also carrying the burden of past failures and inherent fragility.
Okay, now let's contrast that with the American contender.
Right.
The counterpoint. The American entry in Exercise Dracula was the M4 Sherman. And if the Cromwell was hailed, at least internally, as a masterpiece, the Sherman arrived with a very different reputation.
Very different, is putting it mildly. The initial British perception of the Sherman was, well, pretty harsh. Often quite dismissive, maybe even tinged with a bit of snobbery about American mass production versus British craft.
They mocked it.
Openly. Many British officers did. There's a specific insult cited in internal memos from the time that really stuck. They called the Sherman a mechanical refrigerator.
Ouch. A mechanical refrigerator.
Yeah. It perfectly captures that disdain, doesn't it? It implies it's just a utilitarian appliance. Clunky, mass-produced, no finesse, not a finely crafted weapon of war.
And visually, it was different, wasn't it?
Yeah.
Taller, blockier than the Cromwell.
Noticeably so. Physically simpler in its construction compared to the sleek lower lines of the Cromwell. It didn't scream high performance. It didn't have that Rolls-Royce engine pedigree.
It looked like it was designed by accountants, maybe, not engineers focused on elegance.
And you know what? That aesthetic critique, that lack of perceived glamour, that was actually the key to its strength.
How so?
What many British observers failed to grasp immediately was that the Sherman didn't need to look powerful or elegant. It just needed to work. Consistently. Reliably.
So it wasn't just accidentally simple, it was a different philosophy altogether.
A fundamentally different approach to industrial problem solving. You see, while the British engineers were asking, how do we build the absolute fastest, highest performing tank possible?
Right.
The Americans were asking a different question. How do we build 100,000 reliable tanks that work by next Tuesday using the factories we already have?
Okay, let's dig into that. Industrial efficiency. How did the American design philosophy bake in reliability and manufacturability from the start? It wasn't luck.
Absolutely not. It was a deliberate, calculated strategy based on leveraging existing civilian industrial capacity and enforcing extreme standardization.
Okay, give us an example. The engine, maybe?
Good place to start. While the Cromwell had the complex, bespoke Meteor, many Shermans used the Continental R975 radial engine.
A radial engine, like an older aircraft.
Exactly. Crucially, this was a standardized, incredibly rugged, often air-cooled engine. It was already widely used in American aircraft, like trainers and some bombers. It wasn't exotic.
So battle-tested in a different context, but known to be tough.
And designed from the outset to be relatively easy to service, less sensitive to the dust and heat issues that would plague a high-tolerance, liquid-cooled engine like the Meteor in ground conditions.
So instead of adapting a Formula One engine, they used something more like a heavy-duty truck engine, proven, mass-produced, easier to maintain.
That's the idea. Similar maintenance, easier logistics. And that philosophy extended to the whole structure.
How?
The Cromwell required complex armor fabrication, specialized welding hallmarks of traditional craftsmanship, but slow. The Sherman, on the other hand, made extensive use of large, mass-produced cast hulls and turrets.
Casting versus fabricating complex shapes.
Casting is much faster for mass production. Plus, they used readily available, standardized subcomponents, things like suspension units, transmission parts designed to be interchangeable.
So Detroit could churn these out. Factories that used to make cars or tractors?
Or indeed refrigerators. They could adapt their assembly lines relatively quickly. It leveraged the sheer scale of American industry.
And that standardization. That's the key for logistics, isn't it?
Yep.
Interchangeable parts.
It's a game changer. If a Cromwell gearbox failed, you might be waiting weeks for a specialized replacement part from a single, dedicated production line back in Britain. Limited supply.
Right.
If a Sherman transmission component failed, a replacement part, potentially fabricated in 5 different factories across the U.S. Midwest to the exact same specification, could be pulled from readily available stocks near the front line and bolted right in.
That's a massive advantage. And it extends to repairs in the field, too.
Directly. Because the design was simpler, more robust, and made of these standardized modules, it could often be fixed by regular Army mechanics, not just hyper-specialized factory technicians.
So you didn't need a team of Rolls-Royce trained engineers flown out to fix every breakdown.
Exactly. A standard field mechanic with basic training and the right spare parts could perform surprisingly complex repairs, like a full engine swap in just a matter of hours right there near the battlefield.
Okay, so the contrast is becoming really clear. Before Exercise Dracula even starts, you have this fundamental philosophical clash baked into the machines themselves.
You do, the Cromwell. Aiming for individual technical perfection but demanding specialized care and parts, versus the Sherman, built for quantity, ruggedness, and simplified logistics above all else.
And this trial, Exercise Dracula, was set up to determine which of those approaches would actually survive the brutal reality of sustained warfare.
Precisely. Time to put the philosophies to the test.
Yeah.
So the test itself, Exercise Dracula wasn't just, a gentle drive around the block.
No, it sounds like it was designed to be punishing.
It was systematic mechanical torture, deliberately designed to mimic the absolute worst, most arduous sustained conditions of a deep armored push into enemy territory.
And when the Cromwell and the Sherman rolled out from Bovington, how far did they have to go?
They began a staggering, meticulously recorded 2,000-mile endurance run.
2,000 miles on British roads and terrain back then. That's immense for a tank, especially under simulated wartime pressure.
It really is. This was all about endurance, pushing the limits, not about setting speed records. And the level of observation was intense.
They tracked everything.
Everything. The engineers logged every single minute of downtime, every repair, no matter how small, every drop of oil used, every component that failed or needed adjustment. They were building a huge data set.
A statistical deep dive into failure, essentially, designed to expose the breaking point of each machine.
Exactly. And almost immediately, the Cromwell's high-performance Achilles heel, the cost of that complexity became painfully apparent.
It started breaking down.
Constantly. Despite its potential for high speed on a good road, the Cromwell ended up spending an exponentially greater amount of time completely immobile, undergoing field maintenance. The masterpiece was proving fragile under pressure.
Let's get specific. What kinds of failures were plaguing the Cromwell during this 2,000-mile ordeal? It wasn't just minor stuff, right?
Oh, no, not at all. The reports show clusters of chronic, often debilitating issues, things directly related to that high-speed, complex design.
Like what?
The suspension was a major one. The Cromwell used a sophisticated Christie suspension system, great for speed on relatively smooth ground,
Right.
but when subjected to the constant uneven pounding of rough terrain mile after mile, the torsion bars, the road wheels, they just couldn't hold up without frequent specialized adjustment and repair. They failed repeatedly.
Okay, suspension issues. What about the powertrain? The engine and gearbox?
Big problems there, too. As we discussed, harnessing that high-revving Meteor engine for ground mobility put immense strain on the transmission.
The complex gearbox needed to manage the torque.
Exactly. It overheated constantly. That was a clear signal of severe internal stress. It required continuous nursing by the crews, careful driving, and often led to complete component failures requiring lengthy replacements.
Slowing everything down dramatically.
Hugely. And the engine itself, that finely tuned Meteor, even setting aside the gearbox, it demanded non-stop attention.
Because of the dust and dirt.
Yes. Preventing ingress into its complex fuel and lubrication systems was a constant battle. It was fundamentally an engine engineered to be pampered, kept clean, maintained by experts. And war, as you can imagine, doesn't pamper anything.
That level of fragility must have created a logistical nightmare, even during the trial.
Absolutely. And think about the crews assigned to the Cromwell. It must have felt like, well, like trying to drive a fragile race car in a demolition derby.
Yeah. The constant breakdowns, the need for dedicated maintenance teams hovering around, the psychological impact, the frustration must have been immense.
It really added complexity on top of complexity. Some anecdotal reports suggest that keeping just one Cromwell operational often required 2 or 3 highly trained specialist engineers working almost round the clock.
Wow. Meanwhile,
The Sherman,
the mechanical refrigerator, it kept rolling. It wasn't necessarily elegant. It wasn't the fastest on a perfect surface, but it was designed to absorb punishment.
its simpler systems held up better, much better. It's more robust, less complex systems. The engine, the transmission, the suspension, while maybe less impressive on paper in terms of peak performance, proved far more durable in practice. And crucially, when something did go wrong,
It was easier to fix.
far easier and faster thanks to that standardization and simpler design. It maintained operational status through sheer durability and ease of repair.
Okay, this brings us to the numbers, the hard data. You mentioned the key metric was maintenance hours required per mile driven.
That's the one, because that single number tells the story. It translates engineering philosophy directly into strategic viability. How much effort does it take just to keep this thing moving?
So what did the numbers show for the Cromwell?
The numbers were, frankly, shocking for the British team. The Cromwell's sophisticated high-performance design demanded a staggering 0.07 hours of maintenance for every single mile it drove during the trial.
0.07 hours per mile. How does that translate over distance?
Well, think about that 2,000-mile trial distance. That's 140 hours of dedicated maintenance time per tank just to cover that distance.
140 hours.
Yes, requiring large, skilled maintenance crews, specialized tools, a constant flow of specific spare parts, a huge logistical tail just to support its movement, let alone combat operations.
Okay. Now the crucial comparison. What was the figure for the M4 Sherman?
The robust, standardized American contender. The M4 Sherman required only 0.03 hours of maintenance for every mile driven.
0.03.
Wow. Less than half the maintenance time. Less than half the specialized manpower needed. Less than half the strain on the crucial supply chain.
That difference, 0.07 versus 0.03. It doesn't sound huge and abstract, but in practice.
It's not just an engineering statistic, it's a strategic chasm. It's absolutely massive. Think about it in combat terms. Reliability directly translates into presence on the battlefield.
Tanks in the repair depot aren't fighting.
Exactly. If one army's tanks are spending, say, 140 hours being fixed for every 2,000 miles they cover, while the enemy's tanks only need 60 hours.
The difference in available fighting strength becomes overwhelming very quickly.
It does. The Sherman's simplicity meant that the logistical effort could focus more on fuel, ammunition, getting tanks to the fight, rather than constantly chasing down exotic spare parts for temperamental engines and complex suspensions back behind the lines.
So that 0.03 figure, as unglamorous as it sounds, delivered a really crushing reality check to the British engineers and planners.
It proved inarguable that during the attritional grind of total war, a theoretically perfect tank that required constant specialized care was strategically inferior to a good enough, robust, reliable tank that could simply sustain momentum and stay in the fight.
Reliability trumped peak performance.
And the findings from Exercise Dracula, especially those stark maintenance numbers, were
Yeah.
so devastating to the prevailing narrative of British engineering superiority.
They buried them.
Essentially, yes. The final reports were immediately classified at the highest level, stamped most secret. The data was just too sensitive, too politically and industrially embarrassing to be circulated widely. It contradicted everything they believed about their approach.
But behind closed doors, within the British High Command.
The truth was undeniable. They couldn't ignore the numbers. There's a key assessment from Major General Richardson, one of the senior figures who oversaw the trial. He didn't mince words.
What do you say?
He wrote in his formal assessment that the American M4 Sherman wasn't just more reliable. He called it, and this phrase is incredibly telling, he called it industrial perfection.
Industrial perfection, not engineering perfection or combat perfection, but industrial perfection.
Exactly. That distinction is crucial. He wasn't claiming the Sherman was the best tank in the world for a one-on-one duel against, say, a German Tiger. That wasn't the point.
What was the point then?
He was praising the system that created and supported the Sherman. He recognized that American industry had perfected the art of creating a reliable, mass-producible war machine that was optimized not for the drawing board or the parade ground, but for the brutal realities of logistics, mass deployment, and battlefield durability.
So this is the moment where Exercise Dracula really becomes more than just a tank trial. It's a direct confrontation between two national industrial philosophies.
Absolutely. Britain had built its reputation, going back centuries, really, to the Industrial Revolution, on bespoke skill, on individual engineering genius, on technical cleverness and refinement, the very definition of craftsmanship.
Think Rolls-Royce. Think intricate watchmaking applied to tanks.
Right. And the U.S., particularly in the 20th century, had embraced modern, streamlined industrial power. Standardized components, assembly line efficiency, designing for ease of manufacture and maintenance, often called the lowest common denominator approach. But in war, that's often a strength.
And the realization hitting the British leadership must have been crippling.
It was. They realized they could design and build a brilliant, complex prototype like the Cromwell, but they were fundamentally losing the industrial race because they couldn't replicate that brilliance reliably, consistently, and at the immense scale needed to fight and win a sustained, attritional global war.
They were being outmanufactured not just in sheer numbers, but in the operational efficiency and reliability of the final product delivered to the troops.
That's the core of it. The difference between a beautifully crafted machine that needs constant expert care and a machine truly designed for war is that the war machine has to be built by the tens of thousands and fixable by ordinary soldiers in muddy fields.
So what was the immediate impact, even with the results kept secret?
The impact was actually quite swift and pragmatic, even behind that veil of secrecy. The British military didn't suddenly ditch all their Cromwells, of course not. Development continued. But British armored divisions quietly, steadily, and increasingly began to rely on American M4 Shermans, supplied through Lend-Lease. You see more and more Shermans filling out the ranks of British units as the war progresses towards D-Day and beyond.
And the reason wasn't because the Sherman was suddenly seen as faster or better armed than the latest Cromwell upgrades.
No. The primary driver for this increasing reliance was simple: reliability. The supply officers, the commanders in the field, they knew they could count on the Shermans showing up, staying operational, and being fixable when damaged.
They were predictable, sustainable. They offered operational density.
Exactly. Having more tanks available more of the time is arguably more critical in large campaigns than having a few theoretically superior tanks that spend half their time broken down.
So the core strategic lesson from Dracula, even if unspoken publicly for decades, got absorbed into British military planning.
It had to. In a long, grinding war of attrition like World War II, reliability isn't just a bonus feature. It dictates everything. It dictates your logistics, which dictates your operational tempo, which ultimately dictates your strategy.
And that quote from the sources really sums it up.
A perfect tank that can't reach the battlefield is just scrap metal. Doesn't matter how good it is on paper, if it can't reliably get to where it's needed and stay there, it's an unusable asset.
It's the ultimate proof that sometimes the best design isn't the one that maximizes peak performance, but the one that minimizes the chance of failure under real-world stress.
The Cromwell was designed, perhaps, for the best-case scenario, good roads, expert maintenance nearby. The Sherman was designed for the most common scenario, dirt, stress, breakdown, chaos, and the need to just keep going.
So looking back at Exercise Dracula now, the paradox is just stark, isn't it? You have the British masterpiece, this sleek machine powered by the heart of a Spitfire, which ultimately failed its crucial mission of reliable endurance. And then you have the unglamorous American workhorse, openly mocked as a mechanical refrigerator, which delivered this quiet but resounding strategic victory simply by proving it would keep working.
That data, the 0.07 hours of maintenance versus 0.03, it forced the British military establishment eventually to swallow a huge pill of national pride. It forced a reckoning with their entire approach to industrial design and military procurement, even if those lessons took time to fully filter through.
It shifted the focus, didn't it? Away from pure cleverness towards robustness.
It highlighted that efficiency in manufacturing and simplicity in design weren't just cost-saving measures. They were potentially the highest forms of engineering, especially when facing the demands of total war.
And, the implications of this hidden trial, they resonate far beyond World War II tank design, don't they?
Oh, absolutely. Think about almost any complex system you rely on today. Could be software, could be public infrastructure, could be the gadgets in your pocket.
We often get drawn to the latest features, the highest specs, the most complex capabilities.
Right. We chase the Cromwell features. But what we truly depend on, day in, day out, is the underlying Sherman quality. The simple capacity to just keep working reliably, to not break down when you need it most.
That's a really powerful point.
It is. The enduring lesson of Exercise Dracula, I think, is that victory, whether that's on a battlefield, in business competition, or even just in building useful technology, it doesn't always belong to the cleverest engineers who build the most intricate systems.
It belongs to.
Often it belongs to the ones who prioritize designing for durability, for ease of maintenance, for predictable, reliable output. They proved, in the harshest possible way, that robustness, not just refinement, is probably the most critical metric for sustained real-world performance.
So the critical insight here is that complexity, while appealing, often breeds fragility. And maybe rugged simplicity is the surer path to performance that actually lasts.
Well put. So next time you encounter a system, a tool, a piece of equipment that just quietly, consistently does its job day after day without fuss, maybe give a little nod to the humble, reliable Sherman tank.
It serves as a kind of permanent, if once classified, reminder that sometimes the machine that looks like a refrigerator is actually the one that helps change the world.